مساء الخير أعزائي طلبة ماستر الكيمياء العضوية. النهاردة زي ما وعدتكم هنتكلم عن مراجعة عامة عن الموضوعات اللي اتكلمنا عنها خلال الفصل، وكانت كلها بتدور حوالين الإكس راي أناليسيس. وزي ما بتتفقوا معايا إنه هذه الموضوعات يعني من الأفضل إن إحنا لو تتاح لنا إن إحنا نشوف الجهاز نشتغل عليه، يعني بدل ما بنتكلم نظري عن البيكس أو عن السيجنالز أو عن الثيوري بس. فما يعني الأفضل لو أتيحت لنا الفرصة إن إحنا نشوف الأجهزة دي، لكن أضعف الإيمان إن إحنا نشوف فيديو أو أنيميشن بتتكلم عن الجهاز، وبنشوف إزاي مثلا العينة بتتحضر أو بتتقاس على الجهاز، وإزاي الداتا بتطلع. وطلبت منكم قبل كده إن أنتوا لو تقدروا تدخلوا تشوفوا بعض الفيديوهات على هذه المواضيع، لكن يمكن علشان برضو ممكن ان انت تضيع وقت كتير، فانا جمعت لك مجموعة صغيرة من الفيديوهات اللي بتخدم في هذا الموضوع وبتفكرنا بايه اللي احنا كنا بنشتغل فيه ونفتكر مع بعض كده بعض هذه الموضوعات. اول موضوع اتكلمنا عنه لو تفتكروا كان عن الاكس راي فلوريسنس. تعالوا نشوف كده فيديو عن الاكس راي فلوريسنس والثيوري بتاعة الموضوع. وهو فيديو بيتكلم طبعا عن الثيوري اوف اكس راي فلوريسنس وعن what's XRF and how it works. بيتكلم برضو عن ال origin of the XRF signals and how these signals help in investigation and knowing the elemental composition of the analyzed sample.
What is XRF? How does it work? And what is it used for? X-ray fluorescence, or XRF, is a reliable method for determining the elemental makeup of any material, as well as determining the quantity of each material. Modern XRF instruments are easy to use, are non-destructive, and can measure a material with little to no sample prep. This makes XRF a preferred analysis method for a great number of industries, including mining, petrochemical, metals, cement, food and beverage, and R&D. An XRF experiment begins by irradiating a sample material with X-rays from an X-ray source. Every material is made up of many atoms, and each atom has a positively charged nucleus surrounded by a cloud of negatively charged electrons. The electrons orbit the nucleus on distinct energy levels or shells. When X-rays encounter an atom, they're absorbed by the electrons orbiting the nucleus. If the energy from an incoming X-ray is high enough, the electron receiving the X-ray will be released from the atom. An empty electron spot close to the nucleus is not a stable state for an atom, so it will pull an electron from a farther away shell to fill that spot. When this happens, a new X-ray is emitted as an X-ray fluorescence photon, which is unique for each element. The energy shells from an atom are named alphabetically, with the closest ring being K, then L, M, and so on. This atomic structure is described by the familiar Bohr model. The photons emitted from these shells were originally described in a notation by a physicist named Carl Mané-Siegbahn. Appropriately, this is known today as the Siegbahn notation. So when you hear the characteristic lines of elements referred to as K lines and L lines, or K alpha and K beta, you now understand that it all refers back to these two models. By applying the Siegbahn notation, we stated earlier that XRF can not only determine which elements are in the material, but also determine the quantity. The key factors to measuring the fluorescence relies on a careful balance between the instrument's power, sensitivity, and the ability to resolve the data. Each element emits a unique fluorescence. There are two techniques used to separate and identify these energies.
تعالوا نكمل كده من فيديو تاني بيكلمنا عن نفس التكنيكس، بس هيعمل بقى ابلكيشن الأول هيعمل مقارنة بين التو تكنيكس ومميزات كل واحد وأفضلية النوع اللي هو ال WDXRF، وإزاي بيعمل تحليل لكوين قديمة وبيعرف لي العناصر اللي موجودة فيها، والاناليسز كومبليت شيت كده بيبان لك فيه كل الاليمنتس وازاي بنقدر نحددها.
How to measure the elemental composition of a material. Of the sample. For measuring the energy and intensity of the emitted characteristic X-ray radiation, there are two possible spectrometer setups. In the case of the energy dispersive analysis, a detector is used that can sort the energies of photons. This setup is often favored due to its low cost and fast measurement times. Its main problem, however, is low accuracy due to broad overlapping peaks. The wavelength dispersive analysis uses a crystal to select which wavelength radiation actually enters the detector. In that crystal, the X-rays are scattered from different layers of atoms, which means that some beams travel a longer optical path. For a radiation with a defined wavelength, the criteria of Bragg's law is met at a certain angle, and all the scattered beams are in the same phase, which means that constructive interference takes place. So if the angle is changed by moving the crystal and the detector, it is possible to scan in a wide spectral range and find out which wavelength characteristic X-ray radiation comes out of the sample. With such a setup, the peaks are narrower and their overlapping is significantly reduced. Therefore, the accuracy in wavelength dispersive analysis is much greater than in the case of the energy dispersive analysis. The main disadvantages of this setup are longer measurement times and significantly higher cost of the spectrometer. Now it's time for the demonstration, where I will measure the exact elemental composition of this 300-year-old Russian coin. For that purpose, the sample is first cleaned with high-purity deionized water and organic solvents. Next, the cleaned substrate is placed into the spectrometer on a special holder, and the experiment is started. Right now, the sample atoms are excited with X-ray radiation and the resulting characteristic X-rays measured. This process can take tens of minutes or even longer. Eventually, a spectrum is obtained where the energy and intensity of the emitted characteristic X-rays can be seen. Based on that data, it is possible to calculate the elemental composition of the material, and in the case of this sample, we are dealing with a copper coin. The high content of oxygen and carbon originate from the rust layer, while the smaller quantities of other elements, such as arsenic, may indicate that the coin had a colorful history. Measuring the composition of the material, however, is just one option for this system. It can also be used to map the elements on a larger substrate, measure the mass thickness of thin films, or even detect very small amounts of unusual elements, which can be handy in analyzing crime scene evidences. There are also smaller handheld versions of this spectrometer in the market. Although they are less accurate than their larger cousins, they are much cheaper and more comfortable for performing quick analysis.
بعد كده اتكلمنا عن موضوع تاني كان برضو من أهم موضوعات الإكس راي أناليسيز، كان بعنوان إكس راي ديفراكشن. تعالوا كده نشوف فيديو عن الإكس راي ديفراكشن والابليكيشنز بتاعته وإزاي.
My name is Tuesday Kuykendall, and I am the Scientific Instructional Technician for the Materials Science and Engineering Department at the University of Washington. And this is our Focus D8 X-ray diffractometer. The Bruker D8 Focus X-ray spectrometer is used to measure the crystal structure of powders or thin film materials. The X-rays are produced in an evacuated tube similar to a cathode ray tube. An applied current heats up a tungsten filament which liberates electrons. The liberated electrons are accelerated by a high voltage and hit a copper target where copper X-rays are generated. The X-rays exit the tube and are incident on the sample from which they are diffracted into a scintillating type detector. The beam passes through a slit which determines the angular width of the beam. Wider slits give more energy but have wider peaks. Smaller slits give less energy but better resolution. The beam also passes through a nickel filter. The nickel filter removes the K-beta energy before the diffracted beam enters the detector. X-rays at angle theta are reflected from internal crystal planes separated by distance d. The Bragg diffraction results from constructive wave interference when the quantity 2d sine theta is an integral number of wavelengths. A fine powder material contains many crystals located at random angles. Certain crystals happen to be oriented so that the X-ray beam, crystal, and detector satisfy Bragg's equation. This causes a signal spike at specific detector angles. It is important to have a sufficient number of crystals to have an even distribution at all possible crystal orientations. During the scan, the detector is rotated over a range of angles to detect bands of diffracted X-rays produced by the correctly aligned crystals within the sample. So now we're going to discuss sample preparation. For X-ray diffractometry, powder diffraction, it is important to have a well-defined polycrystalline material. And the individual particle sizes of your material should be below 45 microns. You need enough to fill one of these wells, and it should be packed in. And what is important is to have enough of each individual crystallite plane so that when the beam hits it at a particular angle, Bragg's equation is satisfied and you get a peak. This is sort of a statistics issue, and so you want to make sure you have plenty of sample so that all those planes are represented. There's two sizes of sample holders here. This is preferred, this large well here, because, as I said, the more particles that you have represented on this surface in all of the various crystal planes, the better your data is going to be. But often most people don't have this much material, and this will work if your material has been prepared correctly. It's just really important to make sure you have a very fine powder. We have sample holders in here in the lab, and once your sample has been prepared properly, you're welcome to come in and use our sample holders. But we ask that you please clean up after you're finished and that they should never leave the lab. Place your sample in the well and just kind of estimate how much you're going to need. You're going to be pressing it down. And you want to make sure that it's filling the well, but it's still flat with the surface of the sample holder. And you just gently scrape off whatever comes out of the well. And you want to keep it cleaned up, because keep in mind, you're going to put this in and there's going to be 3 pins on 3 places on the sample holder, and if there's a lot of material underneath there, that's going to actually alter the angle that it's sitting at, and you'll get your positions will be off. Just flatten it down. And that's ready to go. Even though it's loose powder, if you've prepared it correctly, it will actually hold together on its own. To verify that you have that, just kind of tip it up at a 45-degree angle and make sure that it's holding. The sample stage is held in place with a pressure plate. The position of the beam is fixed, and therefore the position in the z-axis must be very accurate. The plane of the sample must be the same as the plane of the sample holder that is defined by 3 pins. Once your sample is loaded, you can close the doors. The doors are leaded glass and are part of the safety circuit in the instrument. So we are generating X-rays, and those are radiation and could be dangerous. Radiation doesn't travel very far, it doesn't travel through thick objects, and it doesn't travel through lead. So these are leaded glass, and they have little pins in the handles that will engage mechanical switches in this, right in here, in the door. And then there's also electronic switches in the door in the bottom and the top. What this does is ensures that when you close the door, all the switches have engaged correctly and that the door is correctly closed. If the door is not correctly closed, it will cause the safety circuit to trip, and it'll shut everything down. There's a control panel here, and the exact same set of control panels over there. And there's LED lights that ready, on, alarm, and busy. They're all important to note what state they're in. These buttons up here you must never touch. The only button that you ever want to push on this panel is this big green square button, and that's the door open button. To check, to make sure you've done it properly, just check down here and look and verify that the alarm LED has gone off. 2 of the mechanical things that are really important to watch for is how you open and close the door, because that can trigger the safety circuit, and also how you load and unload your sample. The reason that we're concerned about the safety circuit is that inside our
من الموضوعات برضو اللي اتكلمنا عنها في هذا الكورس كان موضوع السيرفس اناليسيس. وفي خلال جزء السيرفس اناليسيس اتكلمنا عن موضوعين مهمين جدا، اللي هو الاكس راي فوتو الكترون سبكتروسكوبي والاو جي الكترون سبكتروسكوبي. ويمكن في اخر محاضرة اخذنا كان في فيديو برضو اتكلمنا عن التكنيك والجهاز ومكوناته وازاي بيشتغل. تعالوا برضو نتذكر هذا الموضوع من خلال فيديو آخر خاص بالإكس راي فوتو إلكترون سبكتروسكوبي.
Welcome. My name is Carrie Donley, and I'm the director of the Chapel Hill Analytical and Nanofabrication Lab, or CHANNEL, at UNC. Today, we will be talking about X-ray photoelectron spectroscopy, or XPS, which can tell us about the surfaces of samples. If you've ever seen rust, you've seen evidence of surface chemistry. When iron is exposed to the atmosphere, the surface iron atoms will react with water and oxygen to form iron oxide, or rust. Often, the surface of a material is very different from the bulk. Steel is a very strong, durable material, but the rust that forms on its surface breaks very easily. Therefore, understanding surface chemistry is important, especially for nanoparticles. As the size of a material decreases, a larger percentage of the atoms are found at the surface. When working with nanoparticles, the properties of the material can be dominated by the surface properties. The nanoparticle shown here has a total of 147 atoms, and 62% of them are at the surface. X-ray photoelectron spectroscopy, or XPS, can tell us about the surface chemistry of the top 10 nanometers of a sample. The basic idea is that we will hit the sample with X-rays, which will knock electrons out of the sample. We'll measure the energy of these electrons to determine the composition of the surface. The XPS experiment takes place in an ultra-high vacuum chamber, where pressures are typically in the 10 to the -9 torr range. One of the most common X-ray sources used in XPS has an energy of 1,486.6 eV. As a comparison, visible light has energies of only 1.5 to 3 eV. So these X-rays have a lot of energy. In fact, they have enough energy to knock electrons out of the surface of the sample. These ejected electrons travel through an analyzer before being detected. XPS can detect all elements except for hydrogen and helium. An atom consists of electrons that orbit a nucleus. This atom contains electrons in the 1s, 2s, and 2p orbitals. Remember that electrons that are closer to the nucleus, like the ones in the 1s orbital, are held more tightly than those in orbitals that are farther from the nucleus. When an X-ray enters the sample, it interacts with the electrons in that sample. These X-rays have enough energy to remove electrons from the sample. Here, an electron was removed from a 1s orbital. The XPS experiment measures how much energy was required to remove an electron from the sample, which is called the electron binding energy. Since 1s electrons are held more tightly than 2p electrons, they will have a higher binding energy. The binding energy will also depend on the atom that the electron is bound to. Electrons in a carbon 1s orbital have a very different binding energy than electrons in an oxygen 1s orbital. When X-rays hit the sample, they penetrate fairly deep into the sample. Many of the electrons generated will scatter off other atoms in the sample, lose all of their energy, and become trapped in the sample. But electrons that are generated within the top 10 nanometers of the surface have a very good probability of escaping the sample and traveling towards the analyzer and detector. We call this the escape depth of the electrons. Only electrons that escape can be analyzed, and therefore XPS is used to characterize only the top 10 nanometers of the sample. If we wanted to analyze an even thinner portion of the surface, we could tilt the sample in a technique called angle-resolved XPS. XPS gives us a spectrum, like the one shown here. Along the x-axis is the electron binding energy, which is a measure of how tightly the electron is bound to the atom it's attached to. The binding energy tells you what element the electron was attached to, that is carbon or oxygen. On the y-axis is the intensity, or the number of electrons emitted. The peak positions for various elements are well known, and we can interpret the spectrum to identify the elements present on the surface of the sample. Polyethylene terephthalate, or PET, is a polymer often used to make beverage bottles. The peaks in this spectrum correspond to the positions for carbon and oxygen in the PET, consistent with its chemical structure. XPS can also tell us how much carbon and oxygen are present by comparing the areas under each peak. We can zoom into each of the peaks in the survey scan to see if these peaks are really composed of multiple peaks. Let's zoom into the region outlined in red in this graph. There are actually 3 peaks in the carbon 1s spectrum of PET. These peaks can tell us something about what the carbon is bonded to. What affects the binding energy for an element like carbon? Here are 2 different environments that a carbon atom could be found in. Carbon bound to another carbon atom, and carbon bound to an oxygen atom. The binding energy of an electron will depend on the atom that it's attached to, the carbon atom, and also the atoms bound to the carbon. As you can see, the electron binding energy for carbon changes if that carbon atom is bound to another carbon atom or to an oxygen atom. Now let's return to the carbon 1s spectrum of PET to assign the peaks. The component at the lowest binding energy is due to the carbon atoms bound to other carbon atoms labeled A. The peak at 286 eV corresponds to the carbon atoms bound to one oxygen atom, marked B. And the peak just above 288 eV corresponds to the carbon atoms bound to 2 oxygen atoms, marked C. The oxidation state of a metal can also affect the binding energy of an electron. The oxidation state refers to the electrical charge on the atom. Atoms are typically neutral, but if they gain or lose an electron, they can become negatively or positively charged. Let's consider titanium as an example. Titanium metal exists in an oxidation state of 0, and its titanium 2p peak appears at a binding energy of 453.9 eV. In the 2+ oxidation state, 2 electrons have already been removed from the titanium. It is therefore more difficult to remove an electron from titanium 2+ than from elemental titanium, and the binding energy is a bit higher. Finally, titanium dioxide, or TiO2, contains titanium in the 4+ oxidation state, and the binding energy shifts to an even higher value. In general, as the oxidation state for an element increases, so will the binding energy. The titanium 2p data for TiO2 is shown here, and we observe the expected doublet with peak positions consistent with titanium in the 4+ oxidation state. But if we have a very thin film of TiO2 on top of titanium metal, we may be able to observe the signal from both the TiO2 and the titanium metal. Remember, the depth of analysis for XPS is only about 10 nanometers. So if the TiO2 is less than 10 nanometers thick, we may be able to see some signal from the metal below it. In this case, we observe another peak at a much lower binding energy. This extra peak is part of a second titanium 2p doublet that partially overlaps with the TiO2 doublet and is due to elemental titanium. I hope this video helped you to understand that analysis by XPS can provide a lot of useful information about the surface of a sample. Thank you for joining me.
زي ما الست أو الدكتورة اللي كانت بتشرح دي قالت, we hope that our videos can help you to understand and know more information about the techniques which we are dealing with. I hope also that, and I hope this video is helpful to you to know many about our techniques. الحقيقة احنا كده خلصنا الموضوعات اللي عايزين نتكلم فيها في الكورس بتاعنا, ويعني إن شاء الله هنزل لكم بعض الأسئلة على الصفحة, وممكن برضو نتناقش فيها, أو لو حد عنده أسئلة حواليها ممكن يعمل كونتاكت معايا أو يسألني على الصفحة أو تليفون زي ما يحب, ونشوفكم في ظروف تانية بإذن الله.